Okay, good morning, calculus class. Today, good morning, I'm going to be talking about the indeterminate form of a limit and something called L'Hopital's rule. All right? First of all, let's discuss what an indeterminate form of a limit is. The indeterminate form of a limit is any limit that when you evaluate it gives you the answer of 0 over 0 or any type of infinity over any type of infinity. In other words, if I have some limit as x approaches c of some function h of x, if it yields 0 over 0, or if it yields any type of infinity over any type of infinity, we call this an indeterminate form of a limit. Now, if you think about the word indeterminate, it really means you can't really figure anything out, right? Now, sometimes the answer will be some infinity, or maybe the limit won't even exist, right? But sometimes it will. Well, in those cases where I can actually get a value for my limit, we can use a rule to help us evaluate the limit. And it is called L'Hopital's rule. Let's take a look at what the L'Hopital's rule says. Now, does everybody see this function f of x, or h of x? Let's suppose that h of x is equal to f of x over g of x. Well, doesn't that mean then that the limit as x approaches c of h of x, well, that can be rewritten as the limit as x approaches c of f of x over g of x, right? In other words, all I'm saying is I've got the quotient of two different functions in this limit. Well, here's what L'Hopital's rule says. If this produces that indeterminate answer of, say, 0 over 0 or infinity over infinity, then I can apply L'Hopital's rule to actually get a value, if the value exists, right? So here's what L'Hopital's rule says. If I have the limit as x approaches c of one function over another function, well, that answer will be equal to the same thing as the limit as x approaches c of the derivative of the numerator over the derivative of the denominator. Now, notice, this is not saying I am not doing any type of quotient rule here. All I'm simply doing is taking the derivative of the top and taking the derivative of the bottom, which makes actually our life a lot easier, right? Now, again, the important thing here is, remember that your limit, your original limit, as you approach some value of c, you have to start off by making sure that you get some type of 0 over 0 or infinity over infinity, okay? Now, the proof of L'Hopital's rule, if you go into your e-book, you can actually see the proof of this by the esteemed Mr. Larson proving this. Okay? Let's take a look at how we can apply this. Now, let's start with this example right here. The limit as x approaches 0 of sine of x over x. Now, this should seem really super duper familiar to you. I know the answer to this is 1. How do I know that? And how do you know that? Well, golly, didn't we use the squeeze theorem to prove this a while back? Right? Well, now I'm going to use L'Hopital's rule to show this. By the way, before we do that, let me go into my graphing calculator, right? You guys remember, if I wanted to take a look at this, remember the limit is simply what the function's approaching, or what the y value is approaching as you get closer and closer to your value on c, right? So take a look at this. I've typed in y equals sine of x over x, and I've graphed it out. And as you can see, as my graph approaches 1 on the x-axis from the left and from the 0 from the left and from the right, this y value approaches 1. Okay, so we know the answer is 1 from the picture. We know the answer is 1 from the squeeze theorem. Let's take a look at how we get 1 from L'Hopital's rule. All right. Now, the first thing we need to do before we start using L'Hopital's rule, we better make sure that we have an indeterminate form of this limit. So let's see here. If I just simply plugged in zeros, wouldn't I get the sine of 0 over, did I just put a theta? Oh my God, I'm sorry, I'm embarrassed. Don't I get sine of 0 over 0? Well, what is the sign of 0? Well, it's 0, and the denominator is already 0, right? Well, there's that indeterminate form of my limit. So now that I know that I've got the indeterminate form, let's apply L'Hopital's rule. L'Hopital's rule says the limit as x approaches 0 of sine of x over x will be the same thing as the limit as x approaches 0 of the derivative of sine of x over the derivative of x. Right? Well, what is the derivative of sine of x? That's right, it's cosine of x. And what's the derivative of x? It's 1, right? So, I know now that if I plug a 0 in here, not only x, I would get the cosine of 0 over 1. Well, isn't that just, the cosine of 0 is 1 over 1, which is 1. And that's how we can get the limit as x approaches 0 of sine of x over x to equal 1 using L'Hopital's instead of using the squeeze theorem. Kind of cool, right? Now let's take a look at an example where I'm evaluating the limit as x approaches infinity of 3x squared minus 5x plus 4 over 2x squared minus 6x minus 6x plus 1. Now, we know the answer to this. Again, folks, would you agree that this is a limit at infinity, which we learned back at the very beginning of this year, and also you learned in pre-calc? We know that these limit rules at infinity follow the rules of horizontal asymptotes, which would be bottom heavy, top heavy, and equal degree, right? Well, I know the answer to this is 3/2, right? You guys remember that? Remember, if the degree is equal, the limit is just the ratio of a over b, just like the horizontal asymptote. But let's see if we can apply L'Hopital's to figure this out. According to this, if I wanted to use L'Hopital's, I first need to make sure that it's indeterminate. Well, would you agree that that would be 3 times infinity squared minus 5 times infinity plus 4 over 2 times infinity squared minus 6 times infinity plus 1. Now again, infinity is not really a number, but would you agree you're definitely going to get infinity over infinity? That is the indeterminate form. Hence, I can use L'Hopital. Alright, so let's take a look at what L'Hopital's would say. Well, let's see. I know that the limit as x approaches infinity of 3x squared minus 5x plus 4 over 2x squared minus 6x plus 1, that equals the derivative. Well, wouldn't the derivative just be 6x minus 5 over 4x minus 6? Now, if I plug in an infinity, I would get 6 times infinity minus 5 over 4 times infinity minus 6. Oh, wait a minute. That still gives me that indeterminate form of infinity over infinity. Well, think about it, guys. Couldn't we extend L'Hopital's one more time? If I still get the indeterminate form by taking the first derivative, doesn't it make sense that L'Hopital says the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x, correct? As long as it's indeterminate. Well, let it make sense. How do we know that couldn't these have been my original function right here? Couldn't that have been the original function? So if I take the derivative of these, shouldn't that still be equal? Shouldn't the limit as x approaches c of the second derivative of x over the second derivative of g, shouldn't that also be equal? Right? I think that makes sense. I hope it makes sense. So couldn't I apply L'Hopital's one more time to this ratio and get the limit as x approaches infinity of 6x minus 5 over 4x minus 6, wouldn't that be equal to the derivative of the top would be just 6, and the derivative of the bottom would just be 4. Oh, that reduces to 3/2. And voila, there's that 3/2 that we got. All right? Now again, isn't it easier just to use our asymptotes at infinity rule and just get 3/2? It is, but I just want to show you that you can actually apply L'Hopital's not just with the first derivative, but it also will equal the limit would also equal the second derivative as well. So you might have to take apply L'Hopital's 2 times, 3 times to get an actual final answer. Okay. Okay. Let's take a look at one more. All right. Suppose I have x squared. The limit is x approaches 2 of x squared minus 2x plus 4 over x minus 2. Let's apply L'Hopital's here. Well, again, shouldn't this equal the limit as x approaches 2? On the top, would you get, what would that be? 2x minus 2 over just 1, right? And plugging in a 2, I would get just 4 minus 2 over 1. Wouldn't it just be 2? So shouldn't L'Hopital's be 2, right? Okay? And that was pretty quick. But wait a minute. For some reason, I don't know why, I've got this itchy sensation that I just want to look at what this graph looks like. So I'm going to go ahead and type this equation in on my graphing calculator. So I've typed it in on my calculator. And again, let's not forget what is a limit. I'm looking for what are my y values approaching as I approach a particular number, in this case 2, from both the left and the right side. So looking at this graph, let's take a look. I get a little bit of, all right, well, my magenta graph is coming in nicely as I approach 2. Oof, wait a minute, I've got a flaw here. As I approach 2 from the left, it looks like I'm shooting off to negative infinity. And as I approach 2 from the right, it looks like I'm shooting off to positive infinity. It certainly does not look like I am approaching the value that I got earlier. This graph does not support the fact that I'm approaching 2, my y value of 2. So what went wrong? What went so terribly wrong in this problem? Guys, do not forget, and this is the mistake. L'Hopital's is a wonderful, powerful tool, but if you don't use it correctly, you're going to get this problem wrong, right? Ladies and gentlemen, what did I do wrong? Why am I a bad boy? I didn't make sure that this limit was in indeterminate form. If I put a 2 in the denominator, I definitely get 0. But if I put a 2 in the numerator, I would get 4 minus 4 plus 4. Agreed? Well, wait a minute. That becomes 4 over 0, correct? That is not the indeterminate form of 0 over 0. You see that? And that's why I can't apply L'Hopital's rule. So again, I cannot impress upon you enough the importance of making sure that you have an indeterminate form of 0 over 0, or infinity over infinity, or negative infinity over negative infinity, or positive infinity. You have to make sure that you have an indeterminate form first for you to apply L'Hopital's rule. Once you've verified that it is indeterminate, then you can go forward with L'Hopital's. I really do hope that you got this screencast, that it makes sense, and that you enjoy this beautiful weekend. Talk to you later. Bye.